I want to experience zero gravity. And you only have a couple ways of experiencing that. You can either go up to space and experience being in orbit, or you can ride in a smaller rocket that just goes up and back down. You get a couple of minutes of free fall feeling, or you could fly in a plane. People call it the vomit comet. It flies in an arc, and everybody inside is kind of floating around inside until they pull back up and you're pulled back against the ground. For that, you get about 20 seconds. And that's probably the most cost-effective way to do it. It's not as expensive as having to ride a rocket, but I think I've got an idea for a cheaper way to do it for longer than 20 seconds. So here's my idea. If you had a really extra tall building, you could ride an elevator that accelerates really fast up for a while, and then it kind of lets go, and then it's just a free fall. So you feel weightless all the way up to the top of the building, and then most of the way back down until that same point, and then it slows you back down so you gently hit the bottom floor, just like a regular elevator. So nothing's jarring, nothing's dangerous. The machines in the elevator take care of everything. Now, I want to calculate how tall this building would have to be. And I'm pretty sure the world's tallest building is like that tall. So that's not exactly cheaper than an airplane ticket, but I have an idea. Who says you have to build up? If you had a hole in the ground, you only need a building this tall and a hole this deep. Now, isn't it also expensive to dig a hole? Yes, unless someone's already dug the hole. There are abandoned mine shafts that go straight down. They go straight down because they have a cable that drops their little elevator down to the bottom. They're deeper than the world's tallest building is tall. So if you could repurpose one of those mine shafts, we could build a little building on top of it that has all the machinery that we need. So let's see if we can figure it out. Stick with me. I think I can make this make sense, even if you don't like math. There's a couple equations that when I learned about these equations, my world changed. Do you remember the scene from the Lego movie when he finally felt like he could build things, and he saw every little piece of the world as something he could use to build something cool with? That is how I felt when I learned these equations. These are called the kinematic equations. They tell you how fast a thing is going, and for how long it can tell you how far it went, and all that stuff. Your final speed is going to be whatever speed you started at, plus acceleration times time. That sounds really mathy and annoying. Acceleration is basically how many miles per hour per second are you increasing. I'm getting an extra 3 miles an hour every second. Miles per hour per second. People that do math don't like to think of it that way because you got hours and seconds in the same thing, and that's confusing. So they do like meters per second, or meters per second squared. That makes the math easier, but it doesn't make it intuitive. It doesn't make it make sense. Miles per hour per second is an easier way to think about what's actually happening. How fast you're going is just how fast you started going. And then for how many seconds were you accelerating? Well, 3 miles per hour per second faster for 5 seconds. Each one of those 5 seconds, I got an extra 3 miles per hour. So 5, 10, 15. I'm going 15 miles an hour faster than when I started. The other ones aren't as intuitive to understand, but I'll write them down just so you can see them. Okay, X. Think about a graph on X and Y axis, but then you get rid of the Y axis, so it's just X. It's like distance. How far are you from the 0 spot on the graph. So it's even easier than like having to graph something in X and Y. It's just like a number line. Here's 0, 1, 2, 3, 4. Well, I started at 1 and then I went two extra feet. So now I'm at 3 because 1 plus 2. Anyway, that was like probably a flashback to elementary. Anyway, our final position is going to be whatever we started at plus whatever speed you started at times the amount of time you're measuring for this equation plus 1/2 times your acceleration times time. Here, we're 1 foot away. This one actually does kind of make sense. You're a foot away from where your measuring tape starts, and you're traveling at 1 foot per second. That's a velocity, that's a speed. An acceleration would be miles per hour per second. Speed is just miles per hour. So maybe we have a giant tape measure and we go in miles. We're a mile away from home, but we're driving away from home at 5 miles an hour for 3 hours. Here, this is where math people like the numbers to not have a mix of hours and seconds, because here we're in miles per hour. If we measured our time in seconds, if you go for 5 miles an hour for 3 seconds, how far did you go? I don't know. We'll have to convert miles into seconds, and then we got this little fraction of a mile. How fast you're going times how long you're going gives you another amount of distance that you traveled. So you started a mile away, maybe how fast you were going for a certain amount of time gives you another 3 miles. Then here, acceleration times time. Oh, I got it wrong. It's actually times time squared. And if we dig into the math a little bit, meters per second squared. This is something you can always do to check your answers. Check the units. If you multiply it by seconds squared, you've got basically one big fraction with multiplication on top. Seconds squared both cancel. You've got meters, which puts it in a nice way to get an answer in meters, whatever distance unit you're using. Okay, and you can make fun of my handwriting in the comments. Some of the other ones are more complicated, but I'll let you see them. That was extra long. But these are the answer to life, the universe, and everything. I'm serious. These are so cool. We're going to go play with them for a second. Here's what I'm thinking. Here's the ground. Here's a little building. Then we've got a mine shaft. We've got to figure out how deep of a mine shaft. And we could also play with how tall of a building would we need to build. And to do that, we'll need to find out how long we're accelerating, how long we've got free fall, and then how long we're decelerating. How many G's do we feel while we're right here accelerating or decelerating? And how much time do we have in the air? If it's 20 seconds for the vomit comet, what if we try to do a whole 30 seconds? That'll be our goal. To think about it this way, what if we start at the top of the building and we just drop the elevator for 15 seconds? How far would it fall? Whatever speed that is, if we hit that speed going up, it'll go up and just barely touch the top of the building. Maybe we'll make the building a little bit taller than where we're dropping it from. To figure out the 15 seconds, then we'll have the same 15 seconds up and 15 seconds down, and then we'll have the rest of the space here for our accelerating and our decelerating. So this is our distance to accelerate. We'll call it distance A. That's from here to here. Then our distance from here to here, that's our distance that we free fall. So distance F. We're not doing ABC, we're doing A for acceleration, F for free fall. What we already know, gravity, we'll call it G, acts downward, so we'll call it negative, at 9.81 meters per second every second. You go 9.8 meters per second faster every second that you're falling. So at this point, we want to find out the distance that we fell, and we want to find our velocity at this point. Velocity in the middle. Velocity at the bottom is just going to be 0. That's not a backward 6, that's a 0. And then right here, velocity at the top is also going to be 0. We start, and we accelerate, and then we slow down right up to the top, and then we fall back down, and then here's where we start slowing back down so we don't slam into the bottom and get hurt, you know? So we got to add to the list of things we need to know. We need distance A, distance F, and velocity at the middle. It's not exactly the middle, it's closer to the bottom, but we'll call it middle. So for this one, we're going to use the velocity final equals velocity initial plus acceleration times time, because we know our starting velocity is going to be 0, our acceleration is going to be gravity, and our time is going to be 15 seconds, because we're saying how far, if we free fall, what's our velocity after 15 seconds. Our distance F is also going to be how far we fall from there. So that's going to be our final distance is going to be our initial position plus how fast we start out times time plus 1/2 times acceleration times time squared. We're starting out at the top of the building. Velocity is actually going to be 0. Time is going to be 15 seconds. Acceleration is going to be gravity. And time, again, is going to be 15 seconds. We're going to put it into Excel so we can play with the numbers some more. I'm going to show you how to make it cool so we can try out a whole bunch of different things without having to redo the math for every single one. Okay, let's start a new spreadsheet. So here's what we know. Gravity, negative 9.81 meters per second squared. Total free fall in seconds. We're aiming for 30 seconds. The one-way falling time, seconds. Here's where we're going to start using formulas. Instead of me just writing half, what if we change how far we want to fall later? We're going to say this cell equals that cell, but divided by 2. 15. So that way, what if we want to fall for 45 seconds? Boom. It does the math for us. Here's our calculations. We wanted to know distance A, distance that we're accelerating, and the distance that we're falling. Falling distance. We're going to do this in meters. We're going to call this the downward fall distance. Now, we're going to do a cool little trick. We're actually going to name this cell G for gravity. We're going to change this back to 30. We're going to name this cell T, total. That's our total time. And this one we're going to just name T. The equation says your initial position. Well, we're 0 meters away from the top of the building. 0 plus velocity initial, which is going to be 0, times T. I can just type T, and it's like, wait, you want this 15 over here, right? Because you named it T. Yes, good job. Plus 1/2 times gravity times time squared. So it's going to fall a little over 1,000 meters. Let's go find mine shaft depths. And it's got to be vertical in the United States. The deepest vertical mine shaft in U.S. is Lucky Friday number 4 shaft in Idaho. 2.9 kilometers. That's almost 3,000 kilometers. That would work. Deepest vertical mine shafts abandoned. The Red Jacket shaft in Michigan, 9,600, almost the same as the Lucky Friday number 4 one. Okay, we gotta know this. How many feet is this? Convert this thing from meters to feet, please. 3,600 feet. So these are like double the depth. We could totally do this with some of these shafts. We just have to figure out how much acceleration time. This is in
feet. This is in meters. So what's our velocity at the middle? And that's going to be in meters per second, because I promise you, meters are the easier way to do the math than feet. We already figured out that is going to be the initial velocity, which at the top is going to be 0, plus acceleration, which is gravity, times time. So that's downward at 147 meters per second. We're going like 330 miles per hour.
Oh boy, only 45 miles an hour. I know that's fast for a regular elevator, but bro, we gotta go like 330 miles an hour. How fast do roller coasters go? Okay, 150 is the world's fastest, so we gotta break the world record by more than double. We still got a ways to go on this. It'll be like an electromagnetic rocket sled or something. There we go. Now we're talking. 8 times the speed of sound. So this is the G-force guy, I think. He set records for experiencing crazy G-forces. Maybe we could do a rocket-propelled elevator? Who knows? Now, the next goal is to figure out how much acceleration do we need during this portion here. How many G's are we going to feel going up? How many G's are we going to feel coming down? One of the other kinematic equations, one of the least intuitive ones, our final speed, V for velocity. Velocity just means speed in a specific direction. So like negative velocity would be going down. This is the final velocity squared is equal to our initial velocity squared plus twice the acceleration times the distance we travel. Our final position minus our initial position. And we want to find acceleration. So let's go look up how many G's of acceleration a person can handle. How many G's is a roller coaster? Between 2 to 5 G's. Okay, some rides reaching up to 6 G's. That's gonna tell us how much distance we need. We want to find this distance based on how many G's of acceleration we pick. So we want to get everything else on the other side of the equation except for the distance. So at this height, we'll call this our initial position. And at that point, we're traveling initial velocity. The bottom part is our final position. So to do the math from here to here, we use this equation. We just want to get this all by itself, our final position. How far down does it need to be so we can have a reasonable amount of acceleration that we experience? And, fun fact, it'll be the same number of G's going up to reach that speed. So, let's solve for this. This will be a flashback to junior high. Let's subtract this from both sides. Final velocity squared minus initial velocity squared. That's going to be equal to twice the acceleration, x final minus x initial. Now, divide both sides by 2 times acceleration. So now we've got velocity final squared minus velocity initial squared. This is a cool trick that instead of putting numbers into these spots, what we're doing is figuring it out with the variables in place. Like A, we don't know what A is yet. We don't know what V is yet. We can figure out a new formula for the stuff we're trying to find out, and then we can have it ready to put other numbers into if we decide we want to use different numbers. We don't have to redo the whole thing just because we're using different numbers. Now we can just add this to both sides plus this. So our final equation is going to be x final. It's going to be velocity final squared minus velocity initial squared over 2a plus whatever our initial starting elevation is. Cool, let's go put it in Excel. I know I called it Excel, but this is Google Sheets. I like using Google Sheets. We found out people can handle 4 or 5 G's. G is short for gravity. How many times the force of gravity? It said 4 to 5. Let's see if we can do it with 4. We can bump it up to 5. We can. So that's the cool thing about doing it in a spreadsheet. We can just change it when we're done. The equation we found that solved for acceleration distance, that is going to be equal to velocity final squared minus velocity at that middle-ish point. That's going to be squared. And we're going to divide that by 2 times our acceleration. So 5 times the force of gravity. That's why I went to cell B2. We got 2 times that. We add downward distance. Actually, that's going to tell us how far from the ground the bottom of the shaft is going to be. So I'm going to add that in the next cell. So here we need 220 feet. That's not too bad with 5 Gs. This is total, the falling plus the accelerating. Distance equals, oh, one of these is positive, one of these is negative. This should have ended up negative. Just to get rid of all the negatives, so we have one number, we're going to do abs, which is absolute value of this number plus the absolute value of that number. Oh, did I say 220 feet? It's 220 meters. I still need to convert that to feet. Equals, convert this from meters to feet. Yes, that is what I wanted. All right, I did some formatting here and added the acceleration time with this equation down here. Here's our finished calculator. We can change the g-forces here to whatever we want, and it updates over here, shows us the total distance, whether meters or feet, shows us how deep of a mine shaft we need. And right here we can change the free fall time. The 2 mine shafts we looked at were a little less than 3 kilometers, or like 2.9. So can we go 45 seconds? No, that's over 3 kilometers. 42.4. Okay, so it looks like 42 is about as close as we can get to those mine shafts. 42 seconds of free fall. That's pretty good. Let me know what you thought of this video and ways I can improve it. Thanks for watching. Don't be scared to be a beginner at something.